Hi, I'm Bahar Viniche, and today I'm going to present our work with Dr. Berman, Dr. Baron, and Dr. Nourinejad on truck and drone delivery on a circle. I believe that we all, as customers, have experience with the last mile delivery, which is defined by the delivery of packages from the distribution centers to the final delivery destinations, usually customers' doorstep. But what we may not know is that this last leg of delivery process is responsible for about 1/3 of delivery costs. And for delivery firm and customers, the last mile delivery is important in terms of both time and cost. So the goal for a perfect last mile delivery process is to deliver the packages as quickly as possible at minimum cost. So even marginal improvement in the current last mile delivery process will help the delivery firms, but the emergence of new technologies will totally change this game. Drones are known as the future of delivery industry. In the figure, you can see the drastic increase of the market share of drone delivery from 2016 to 2026. Using drones by delivery industries will shift the traffic from roads to sky. It will help the public by decreasing the inner city traffic, in addition to allowing drones to fly at higher speed and speeding the delivery process. These advantages, in addition to the lower operational cost of drones, make it a good candidate for addressing the last mile delivery. You can see some example of firms that are currently practicing the last mile delivery using drone delivery, or is going to use the drone delivery for some part of their services. And I believe that you can add many more examples to this list. On the other hand, drones have some operational limitations and critical constraints. For example, their limited flight range or the payload limitation. So a hybrid fleet of truck or any other vehicle with drone would be the best practical way to solve the last mile delivery problem, because in this way, by using a hybrid truck drone fleet, we can overcome the short range and payload limitation of drone as well. This video is by UPS, and it's almost the same for any other firms practicing hybrid truck and drone delivery, in which a truck travels from the distribution center containing both drones and packages. This will help for overcoming to the drone payload limitation, because a drone doesn't have to carry all the packages with itself from the distribution center. And the truck will stop at some point at its path, launch the drone with the package. Drone will deliver the package to the customer's doorstep, and then a truck will retrieve the drone at some other point in its path. So it will also help to overcome the drone range limitation, because it travels some part of the path in the truck. There has been a wide range of academic research on drone delivery, or even on truck and drone delivery, using different methods and approaches like network design or solving VRP or TSP. For example, in this article by Carson and Son, they tried to solve this problem by a hybrid fleet of one drone and one truck to solve a TSP problem. And in this figure, you can see different scenarios based on different battery limitation. And in the left, it's the it has been considered that the drone battery limitation is 0, so drone can't fly at all. So you can see that there is no drone flying. And in the right scenario, and they increase the battery limitation, and in the right you can see a scenario in which the battery limitation is equal to its infinity, so drone can fly as much as it wants. We, on the other hand, decided to use a stylized model. We considered a stylized model to address this problem because stylized models are abstraction of reality, which avoids the unnecessary complexities while providing a powerful tool for analyzing different scenarios and proposing different policies. I also want to mention a recent review article on the future of drone delivery. This article mentioned that the most challenging problem of a hybrid drone and truck delivery is synchronization between the operation of different vehicles, trucks and drones. And the scheduling between these two operations are the most challenging parts of hybrid fleet and drone models. This research also strongly encouraged the researchers in this field to consider the drone operational limitations, which are related to flight range, battery capacity, battery life, speed, and payload limitations, which is what we clearly addressed in the current research. So we consider a stylized model of N recipients on the circumstance of a unit circle and depot as at the center of that circle. As I just mentioned, we consider that truck leave the depot with both drones and packages. It travels a distance of R, then travel in an inner arc and launch the drone to do the deliveries. So truck stops at some points at its path, launch the drone or drones, and drones do the deliveries, and then truck retrieve the drones in another point in its path. We tried to model this problem with some limited number of decision variables and to show different scenarios just based on these decision variables. The first variable is the travel distance of the truck. And the next one is the number of recipients who is going to be served by one truck. So truck travel from the depot travel a distance of R, and it's responsible for serving xt number of recipients. Then truck stops at M hubs at its path. And at each stop, at each hub, truck can launch or retrieve the drone or do the both launching and retrieving the drones. And at each launch hub, drone will launch a batch of Q drones at once. And it will retrieve this batch after we stop. So I'm going to show you some scenarios based on these decision variables. Also, I'm going to introduce two important concepts of relaunching and multi-launching. Here in part A of this figure, you can see multi-launching, which means launching more than one drone at once. Here you can see that truck launched 3 drones, and so Q is equal to 3. And then a truck will retrieve the drones after just one stop. So V is equal to 1. And we have total number of 2 stops here. And part B of this figure show relaunching, which I'm gonna explain. Here truck will launch 1 drone, Q is equal to 1. And it will retrieve that drone after 1 stop, so V is equal to 1. But here, then a truck relaunch this drone again and then relaunch it again. So we have 1 drone and this drone fly 3 times. And here we see that we have total number of 4 hops. M is equal to 4. And in the part C of this figure, you can see a combination of relaunching and multi-launching. A truck launched 3 drones, retrieved them after 1 stop, relaunch them, and retrieve them again. In part D, you can see another scenario in which V is not equal to 1, which means that, for instance, here V is equal to 2, which means that truck will retrieve the drones after 2 stops. In the scenario, truck launched 3 drones at the first hop. At the second hop, it launched another 3 drones. At the third hop, it retrieved the first 3 drones, and at the last hop, it retrieved the second 3 drones. So we have total number of 6 drones here, but Q is equal to 3 because at each hop, truck launched just 3 drones. We have 2 important set of constraints in our problem: the scheduling constraints or synchronization constraint, and the operational constraints. And I believe that I somehow mentioned these 2 set of constraints, but I'm going to explain more them in detail. Operational constraints are both related to truck and drones. The one related to truck operations is truck capacity, which is limited. And 2 other important constraints are drone operation, the drone range limitation and capacity limitation. We also have the scheduling constraint for synchronization, the operations of trucks and drones. The first constraint is responsible to ensure that truck is at the retrieval point previous to first drone. Obviously, drones will fly different passes. So truck should be at the retrieval point prior to the drone, which is flying the shortest pass, because we don't want that drone to remain idle in the air. Also, trucks should wait at the retrieval point for all the drones to be there, even for the ones who are flying the longest path. Finally, our objective function, this is our mathematical model, and in the right, you can again see the decision variable if you need somehow a reminder. We first want to solve the problem for a fixed number of NT and ND, fixed number of drone and trucks, and obtaining the optimized value, and then we will solve a bigger problem to find the optimum value for the number of truck and drone. So for the first step, we solve this objective function, and the goal is to minimize the delivery time. In the first term, you see the traveling time, and in the second term, you see the waiting time, the truck waiting time, as I just explained. I should also mention again that drones will fly different paths, and this is why we have Lmax and Lmin. And here, for example, in the drone range constraint, you see that even the drones that fly the largest paths, and even in case that we have relaunching, the total flight distance of drone should be less than its range limitation. For the next step of our work, as I mentioned, we want to go to optimize the fleet and driving closed form expression, and then obtaining some meaningful insight over the problem. And then we want to consider a random customer distribution. So instead of N being a fixed uniform distribution, it would be a random distribution. Thank you for your attention.